So if you have in class number 8, get that out. The goal of today's class is to try to get a little bit better intuition in what is happening as far as head loss, specifically minor losses. Because I think our intuition is pretty okay for major losses, like why is pressure decreasing or why is energy decreasing down a pipe? Well, because of like viscosity and there's friction with the walls. Okay, I think we can get there. When you look at a table like this of the minor loss coefficient, like why are different types of things, like where are these numbers coming from? Maybe more especially this chart here. I think there's some really interesting stuff. This is for an expansion or a contraction. So what it's looking at is the minor loss coefficient for an expansion or contraction. This top line for an expansion, the bottom line is for a contraction. They're on the same scale. So one of the things that's kind of interesting, expansions have more loss than contractions. And it turns out this is like a general rule. Expansions will have more loss than contractions. So we'll look a little bit at some videos to try to get a better handle on physically what's happening. Because I think some of this goes against our first pass intuition in terms of what's happening with flow and pressures and velocities and how all of these things are related. Like you can see them in an equation, but connecting all of that stuff, I think, takes an extra step. So that's what we're going to be looking at. We're going to be looking at it in the context of a few videos. So, right, what we watched last time, we watched some videos of cavitation. Remember watching those? So hopefully that kind of covers at least some of the first part. We'll be able to go back and hopefully with some of the stuff that we watched today, you'll be able to better interpret what was happening in those videos from last class and what was better happening on this first page. But what we're going to do is flip over to the second page, the second problem. We're going to watch like 5-ish minutes of this video. I'm going to pause it at a lot of different points to explain what exactly we're looking at. It'll be a little bit before you get to part C, so you can just sit back and watch for the first little bit, and I'll pause it when we get to part C. Part A and B, you can probably answer without watching any of the video, hopefully. But this is looking at pressure fields and acceleration. So he'll start by talking, just kind of reviewing some stuff about Bernoulli's equation.
In an incompressible, steady, non-viscous flow, Euler's equation has a special integral called Bernoulli's integral. Along each streamline, the sum of the static pressure and the dynamic pressure is a constant. This sum is called the stagnation pressure. On any streamline, where the velocity is high, the pressure is low, and vice versa. The highest possible pressure, the stagnation pressure, occurs where the velocity is zero. A very large reservoir supplying a flow to a duct system is itself a stagnation region. Here is the stream flow past the one body with a central stream tube marked by hydrogen bows. The widening of this stream tube tells us that the flow is decelerating. The singular point where the central streamline reaches the nose is the stagnation point.
There.
The speed is zero. On both sides of the unique stagnation streamline, the fluid decelerates, but not to zero speed, and then slides around the sides. The stagnation point is put to practical use in a pitot tube. The hole at the nose measures the stagnation pressure of the particular streamline reaching the hole.
Right, and again, we have previously in the class related stagnation pressure. That's like the total mechanical energy that the flow has.
We find tubes at the upstream and downstream cross sections of the contraction. And these are the static pressure manometers we had before.
Okay, so they've shown this before, so I just want to explain what you're looking at. You're looking at a channel, it's a two-dimensional kind of box that goes from being fairly wide over here. So it's flowing from left to right. It goes from being fairly wide, there's a contraction down to a fairly narrow channel. And then sticking out at the top, we have two manometers. Those are the two labeled stat. Those are measuring static pressure. And then sticking down into the fluid, we have two pitot tubes measuring the stagnation pressure. So you're a large channel up here and it's going down to a fairly narrow channel.
The difference between the stagnation pressure and the static pressure is the work in dynamic pressure. So this is because of the action, the dynamic pressure and the static pressure change. But the sum of the two, the stagnation pressure, remains constant, which is what Bernoulli's integral told us. Bernoulli's integral also explains how we can produce suction by blowing.
We'll talk more about this later.
To show how Venturi can produce flow pressure, we have formed half of a symmetrical Venturi with central test section as one projectable wall. A gradually static. Here is set up for test. These are inclined manometer boards to show the pressure.
Okay, so he'll explain it, but I want to also explain in a little bit more detail what you're looking at, because otherwise it's hard to figure out what's happening. So they have this big like circle thing, that's a settling tank. So basically they're trying to get all of the turbulence and stuff out. And then they're pushing the fluid through the thing that we were just looking at, like top down, through that channel. Along one wall of the channel, it's just flat. The other wall of the channel, he can basically move to make any shape that he wants. And then there are holes along both sides of this thing, which are connected to just tubes that go up these little inclined V planes. So there are tubes along, like all along this wall that just go up this inclined plane. They're just acting as manometers, measuring the static pressure. So the farther they are up the wall, the higher elevation, the larger rho GH is, the higher the pressure. So when what you're looking at, we'll look from the top down, and the length of the tubes, you'll be able to see the fluid. The height that's reaching is just measuring the static pressure, measuring P.
Pressure distribution on the two walls. We will observe the length of the water columns looking down from a position directly above. Now the flow is steady. We will look first at the pressure distribution on the straight wall. Continuity tells us that because of the area of contraction, the velocity increases to the throat.
Okay, so again, just to not to belabor the point too much, but you're coming in at this this width. The channel is the same height everywhere. So the area is looking at just the width here in 1D. You're coming in at that width, it's getting pinched to a smaller width, and then gradually expanding back so that down here, where this last one is, we're back to the same width that we were when we came in. So you start coming in at one width and then going back to the same width down at the end. This is the left-hand side. Apologies for kind of a bad picture, But this is supposed to be the left-hand side of part C.
And this is called a packet drop. Downstream of this flow, the area increase produces a velocity decrease. And this causes the pressure to rise. At the upstream and downstream ends, where the cross-sectional areas are equal, the average velocities are also equal, and Bernoulli's integral will predict equal pressures. But the downstream pressure is actually somewhat less than the upstream pressure. This difference is due to viscous boundary layers, whose behavior we must always keep in mind, even when we pretend viscosity is absent.
And so he said we come in with some pressure, some amount of total energy, pressure and velocity. We get pinched down to this at this throat, and we have to exchange pressure for velocity. Pressure goes down, velocity goes up. Then we reverse that exchange as we go from here at low pressure, right here, there's our lowest pressure. Our fluid slows down, so we're losing kinetic energy. So we gain back our pressure. And you can see that we gain back our pressure. We don't gain it all the way back up to 6. We're at like 5 and a little bit on that scale. So why aren't we gaining all of it back? Well, because of head loss. So you're directly seeing, in this image, you're directly seeing the head loss. And just like take a second to marvel, like he's just drawing on this thing with like a Sharpie. I don't know, I think this is a wonderful visualization with like all analog technology. Kind of fun. We'll dig in a little bit more why that happens in the next video.
And they were very helpful in recovery in the diffuser.
Okay, so what we change is now this is the one on the right-hand side. We changed from kind of a gradual expansion to a really rapid expansion. So we contract and then we expand now really rapidly, whereas last time it was much more gradual.
Before. Even a very small amount of density, if it leads to boundary separation, can produce very large changes from a truly non-viscous situation.
Okay, so he just mentioned the word boundary layer separation. I don't expect you to know what that is. This is actually a nice image of it. We'll dig into what that is in the next video. But just so hopefully, right, these are kind of the two pictures for C that you should have. So obviously for this one, for the faster expansion, we're seeing visually, right, we went from getting up to this pressure here, like 5 and a little bit, to now 4 and a little bit. So we have a pretty significantly larger amount of head loss when we have this faster expansion. Looking at this pressure, just flip back to problem 1, your diagram of this little valve. See, kind of looking at this, looking at the picture you drew, see if what you drew was correct or if it should be erased and amended a little bit. Maybe you're happy with it, but maybe, but I mean, this is kind of like a valve would be an extreme version of this where it's like a very abrupt contraction. So what would be happening with an even more abrupt contraction with the pressure? Okay, the,
The separation can produce very large changes from a truly non-viscous situation.
so this next thing that we're going to look at is another called a Venturi. We'll flip over to the next page, the third page, and just start thinking about how something like this would work. And while watching the video, and then we'll take a few minutes after that to work on that.
In this experiment, water flows through a Venturi that discharges through the atmosphere. As we increase the flow, all the pressure differences increase with the square of the velocity, and the pressure of the throat decreases. The gauge shows vacuum, and the pressure of the throat is now about 20 inches of mercury below atmospheric. Watch the throat.
So this is atmospheric pressure. It's hard to read. This is like zero pressure.
These patches that form are actually steam. This is cavitation. When the absolute pressure water changes to steam. And
So you can't read the gauge really, but this line right there, you can kind of see a little bit darker. That's 30 inches of mercury. That's like zero pressure. We get stuck at like 29 because that's the vapor pressure of water. 1 inch of mercury. So that last little bit, we get stuck there because that's where we actually start boiling the water. So you can see we basically get low enough pressures here that we're getting cavitation and seeing this boiling effect that we talked about last time.
And the subsequent collapse of the bubble, which you can hear, creates enormous stresses in the wall. Mechanical stresses owing to the implosive collapse of cavitation bubbles on a surface do great damage to hydraulic machinery.
Okay, we'll pause it there. So see if you can spend, I'll walk around. If you have any questions on part 3, but see if you can't. I don't need equations, but kind of a qualitative description of how a Venturi system like this works. And then if you can't think of any off the top of your head, take out your phone and Google like a couple real world places where this effect either happens by accident or we try to design a system to utilize this effect to do something. I can tell you one, my coffee maker uses this. This is the Venturi effect to froth milk. So this I'm kind of assuming is, let me go back to. This is really the system that we're looking at. So he's blowing air from right to left. It's discharging out here at atmospheric pressure and it's causing a suction down at this end where he's like sucking liquid up that straw. So you're not necessarily going to get cavitation in every Venturi, but you will get a low pressure at the top. Like whether you get cavitation depends on what the fluid is. Obviously, if it's air, you're not going to get cavitation. It also depends on what the velocity changes are going to be. So where's your lowest pressure? So you're going your atmospheric pressure here. Because you're just turning the atmosphere. So there you have to be going from there to there, you're slowing down. So pressure has to be going down. So that's going to be that's causing suction at this point here, because this is the below atmospheric pressure. You're always going to be, you're always going to be exchanging pressure and velocity. Velocity goes up, pressure goes down. The lowest pressure is going to be at the contraction, where the velocity is highest. Yeah, potentially, but I guess that's more just like a hand radius explanation. So you're coming in here from high pressure, so this kind of whole region there is going to be low pressure. And what's going to cause it is your atmospheric pressure here. So you go from here, you have to pop in pressure because velocity is holding back. So that's kind of an introduction of that spot. Anybody finding interesting places like the Venturian effect is used or happens on accident? Has anybody ever like walked past a building and tried to open the door when it's windy and it's super hard? The Venturian is your atmospheric pressure inside the building and your atmospheric pressure out there. The building will go in flows, exchange pressure for velocity. So you create a low pressure actually outside. So it can make it really hard to open the door because there's like a vacuum that's formed.
Or if you're like inside and you open it.
Yeah, it was inside and just like opens like crazy. The same thing because you wind is creating a low pressure on the outside of the building. Also, why cities are super. One of the reasons why cities are super windy. You get wind blowing between buildings. Then it like causes suction, so it pulls in air down alleyways and like side streets and stuff. You're blowing all kinds of fun directions. Any other places where they're found? It's used like in airbrush painting. Has anybody ever done that? Like seen like a paint sprayer, a lot of times they'll use the Venturi effect. The carburetor on an engine will use the Venturi effect. They're used actually quite a bit on airplanes because airplanes are going really fast. So they'll use the Venturi effect. They'll use Venturis to get basically suction for free. So it's used in a lot of different places where you need some vacuum and you can get it essentially for free if you have a velocity. Okay, neat. So David says he's done like chemical mixers basically with the Venturi effect. But also sometimes in chemistry labs, like for easy vacuum. Okay. Okay, so there's some more. This is a fun one. So this isn't on your sheet, but this is, I think, just kind of fun just to see how sometimes fluids can be counterintuitive. Right, so he is not sucking. He has a clear plastic disc with the tube coming out of the top. He's blowing air out of that tube. He's not sucking it up. He's blowing air out of the tube. And then watch happen. This like opaque white disc is like just a lightweight plastic disc.
To see how
So that's when he's blowing air out. It lifts up.
we've implemented this by 20 times. Testing and harder to scale. 3 double spacers keep the disc and plane apart. This suction tube shows atmospheric pressure. In these tubes, water level rises because of not below.
Okay, so he's blowing out of this tube. So the rightmost manometer is measuring the pressure at the center. And then as you go from right to left, it's going from like the center to the outer edge. So what is the pressure going to do from the center to the outer edge? Any ideas? What's it going to do right at the center? We've done this a whole bunch before, right? You have fluid flowing, and it's going to crash into that disc and come to a stop. So what's the pressure going to do? It's going to go up to the stagnation pressure, right? So that should be above atmospheric. But then what has to happen? Outside is atmospheric pressure, right? It's 1 atmosphere. So your high pressure at the center, but then you have to, like for the air to get out, it goes from, it's going to spread radially out of that disc.
Testing and harder to scale. 3 double spacers keep the disc.
Right, so the air is coming in right at the center and it has to spread out radially. As it spreads out radially, it has to slow down. When velocity goes down, pressure goes up. So pressure has to be going up to atmospheric pressure at the outside. We'll look at what happens.
This suction shows atmospheric pressure. In these tubes, water level rises from the present ground below. At the axis, the pressure is greater than atmospheric. I am not equal to the dynamic pressure of the air.
So that's the stagnation pressure.
When we remove the plate, it is lifting. And rises to atmospheric pressure at the outer edge. The reason for this is that the through-flow cross-section area between this increases with radius. This area increase causes a fluid deceleration, and by reducing growth, pressure rises.
Isn't that wild? So force is equal to pressure times area. So you have a really small spot in the center at high pressure, which is pushing the disc away. But most of the disc is actually below atmospheric. So that's trying to suck the other one up. So the net effect is actually that, you're blowing air out and you suck the disc up. Kind of a wild effect. Okay, so here's another fun one. This is, we're flowing from left to right. You just tell me what's going to happen. We're flowing from left to right. And then we have a couple drains here. And these manometers are measuring the pressure along the way, right? So what he's going to do is he's going to open up those 4 little taps and let liquid drain out the bottom. So what is the pressure going to do from left to right? Stay the same, go up, go down. Okay, hands raised for the pressure is going to stay the same in that main line. It's not going to stay the same. Hands up for the pressure is going to go down. So it's highest pressure here, lower, 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 lower. Maybe. Okay. Hands up for it's going to be the lowest here at the left. And as we drain out, as like it's going to drain through the tap, then the pressure is going to be higher after that. Going to drain through the next one, it's going to be higher. Drain through the next one, it's going to be higher. Does anybody have an explanation, or are you just raising your hand? Got to be one of those, right? Think through it. What happens? So pressure and velocity, how do they relate? Velocity goes down, pressure has to go up because of conservation of energy. So what's happening to the velocity in this main line as we go from left to right? It's decreasing. Why? Because you're draining it. So what's going to happen to the pressure?
It is shown by the water levels in these number figures. With the bleed valve storages, the average water velocity is the same at all cross sections. And there is a very slight pressure drop due to viscous force.
Right, you can see the head loss from viscosity.
I'll reduce the volume flow at successive sections by bleeding water from the manifold.
Isn't that wild?
The pressure now rises. Since the area is constant, the velocity is proportional to the volume flow. Therefore, the velocity decreases. It is this streamwise deceleration which produces the streamwise rise in pressure.
Isn't that wild? It's crazy to me. It's totally opposite of what, if you didn't stop and think through what the math tells you, it's opposite of what you would think. You'd be like, oh, we're draining it out, the pressure's going down. It's exactly the opposite of what's actually happening. Okay, so we're going to look now in this next video a little bit more in depth into what's happening in this system and why it's doing what it's doing. So what we've seen is when we look at, okay, we have a contraction and an expansion. We know at the contraction, that's where we're at our lowest pressure. And then at our expansion, velocity goes down, pressure goes back up. But it doesn't go all the way back up to where it used to be. So we're going to look a little bit more in depth at like what's actually happening in the fluid that's causing the head loss that we see. Okay. So we're going to look, just flip over to the last page. 4A, you're basically just redrawing what you drew on problem 2. So just take a second to redraw that, kind of so that you have a baseline. That's at least the pressure part. And then we'll draw a little bit on the thing below. Okay, what we're going to be looking at a little bit in this is what we call boundary layers. We haven't discussed boundary layers, so I think this image is a nice introduction. If you've taken heat transfer, we've started talking about boundary layers, but if you haven't, I just want to show the kind of this first snippet so that you know what we're talking about. So this is just a normal flow. You're looking at just streamlines for like a nice laminar flow.
Perpendicular to the streamline shows that the unobstructed flow is photoresistant. Here's the flow over a plate. The flow is two-dimensional and limited. Upstream of the plate, the flow is still uniform, but in the fluid layers near the plate, the velocities are much lower and vorticity is present. Yeah,
so the thing in the middle is just a two-dimensional plate. We're looking at this.
The boundary region adjacent to the plate, the shearing forces and inertia forces are of equal importance in determining the motion of fluid elements. Outside of this region, the shear stress can be neglected.
Okay, so if we pause it right there, when we talk about boundary layers, what we're talking about is the area near a wall where we kind of are feeling the no slip condition. Right at the wall, you can see it here pretty dramatically. At the wall, our fluid comes to a stop. Far away from the wall, it's like nothing happened. The boundary layer is this thin layer of fluid, kind of, I'm circling it here. This region close enough to the wall that you feel the effects of what's happening at the wall, that you're slowed down kind of by the no slip condition.
The thickness of the boundary layer increases along the length of the plate. The bubbles correspond closely.
Okay, so it's going to look something like this. If you looked at the velocity, it's going to be slowest near the wall, and then far away, you haven't really felt any of the effects yet. And this region where you're slowed down by the wall is the boundary layer. Most of the flows that we've talked about in this class so far have been like inside of something. And a lot of times there, the boundary layer extends like basically through the whole pipe because everything feels some effect of the wall. But if you think of like flow over top of an object, the air, like if air flies over top of something, the air really far above it, like keeps moving on its merry way as if nothing happened. Only the air right at the surface of the object or just near the surface of the object is actually feeling anything, feeling that there's an object there. The air right at the surface is coming to a dead stop, and viscosity is like dragging on the air just above it and slowing it down. So that's like physically what's happening. So this fluid's coming to a stop and viscosity is dragging on the fluid right above it and slowing it down. Okay, let's jump to up here to 11 minutes.
However, in most flow situations, there are regions of decreasing pressure and regions of increasing pressure in the flow direction.
So we're going to look at what happens when rate pressure is not the same everywhere, like we were just talking about.
In the flow direction. We will use this 2-to-1 flow contraction and watch the boundary layer along the flat side.
Okay, so this is a contraction. So what do we know about the pressure? Well, as velocity goes up, pressure has to go down. So it's going to be high pressure on the left side, and then pressure is going to go down, and it's going to be low pressure on the right side. So pressure is pushing from left to right, right? So it's pushing the same direction that everything is moving. Pressure is pushing it, and velocities are going up. So we see that a little bit. You can see that the streamline too. You can see it goes from being, say, that far away from the wall to being like half as far, which again would tell us that the flow rate between that streamline and the wall stays constant, so velocity goes up. You can also see, like here, the fluid is moving relatively slow next to the wall. Pressure is pushing us down this contraction. So down here near the wall, everything is moving pretty fast. Okay, so he'll talk for a little bit about stuff that's we're kind of glossing over a little bit. So we'll kind of jump ahead, but you can think when you're going on a contraction,
It is the boundary layer would be generated within the
pressure is pushing in the direction, the same direction that the fluid is going and keeping things moving along.
combined flow line at the end is relatively fast because they have a flow pile as well as the boundary layer. This is the future. using vorticity logic. On the other hand, in the vertical channel,
Okay, so now our channel is going, instead of contracting, it's diverging from thin to relatively wider. So what's happening to pressure? It's decreasing from left to right. So what kind of forces is that applying on our fluid? It's applying a force from right to left. Right, so pressure is pushing against our fluid flow, pushing that way. It's pushing from right to left, causing our flow to slow down. Right? So we'll look at that. You'll be able to see it should be slowing down from left to right. Right? You can kind of think of it like the inertia of the fluid is carrying it from left to right. Pressure is applying a force, which is resisting that motion and causing the flow to slow down, go to a lower velocity.
the boundary layer becomes fixed with a corresponding decrease in wall shear. In this case, we have an unfavorable pressure gradient. The increasing pressure associated with the decrease in relation to velocity decreases the velocity in the boundary layer. So velocity gradient and shear stress are less, and the boundary layer is fixed. At a larger angle, the decrease in velocity is so great that somewhere.
Okay, now this is a really important image to look at. What's happening like right there near the wall? Our flow is turned around and started going in the wrong direction. Why did it do that? Well, let's think about what's happening with what are the different forces in the system. So our channel is diverging, it's getting wider. So we're high pressure on the left and low pressure on the right. Or sorry, low pressure on the left, high pressure on the right. So pressure is pushing from right to left, pushing against the flow. Okay, so it's a force causing velocity changes. So if you're a fluid particle just here happily moving along in the center, like from here to here, you just slow down a little bit. And you move along on your merry way a little bit slower than you were before. If you're a fluid particle that was like near the wall, you were moving really slow to begin with, right? You were hardly moving at all. So now you were hardly moving, you didn't have a whole lot of inertia, and now pressure is pushing on you. It can push so hard that you come to a stop and turn around and go back the other direction. So right, the fluid like just above you, right? If you think of, okay, why didn't that happen in this case? In this case, where we had a very gradual change, pressure was changing from left to right and pushing against us, but it was only a little bit because it was a gradual change. So in this case, the slow fluid that's right near the wall, it's slow, but it doesn't get stopped because it kind of gets dragged along with everything else because of velocity, because of viscosity, sorry. So viscosity, the faster moving fluid in the center has enough viscosity to drag everything along with it, even the slow fluid at the wall. When we go to a system, like this, the pressure gradient is so much that viscosity can't keep dragging that slow fluid at the wall along, and pressure wins out and turns it around and pushes it the other way.
Along the wall, velocity gradient normal fluid becomes zero, accompanied by a local reversible flow immediately downstream of the point.
We call that boundary layer separation.
The fluid, which was in the ocean of water, is no longer in contact with the wall and is separated from it by the region or earth of the circulating flow.
So you can see now in this area, you get some turbulence, you get vortexes and a bunch of swirling.
On the wall, when you move it, something down the fluid from the region of flow reversal is called separation flow. The wall shear stress is in there. Here is the point of separation of the laminar boundary.
So you can look, the separation point, you can see the velocity kind of at that first layer. Right at the wall, the bubbles don't move at all. There's no velocity. Like this part is straight up and down. So pressure is pushing from the right. Viscosity is trying to drag it the other way. And those two forces are equal to where the fluid comes to a stop. Then pressure wins out, turns it around, and starts pushing it backwards in the other direction. Okay, so what does that have to do with what's happening here? Well, think about, so in this channel, you're diverging really quickly. So the pressure change as you start to step, like your lowest pressure is here. If you go just a little ways further along, the pressure is pretty big there. So it's pushing really hard, slowing down the flow and causing the flow basically to come this way. And then it's not able to stay stuck to the wall there. You guys have visualized this in your everyday life. Everybody's like stuck their hand in the pool and like pushed their hand. And what do you see happening behind your hand? Right? The water doesn't go perfectly around your hand and then come back together and stay like nice and laminar unless you're moving your hand super slowly. When you move your hand, there's an area of turbulence behind your hand. There's a wake. Right? When you push your hand in the water, it leaves a wake behind it. The same thing is going to happen here. Fluid's going to come this way and come up, and then boundary layer separation is going to happen because pressure is basically winning. Pressure gradients are winning over viscosity. And what you're left with is this shape will leave a big wake. And all in this region here, you'll get turbulence and mixing. And basically the fluid is going like this. Like you have all of the viscosity from those fluid layers rubbing against each other, causing heat. So why do you end up with a huge loss in pressure? Because you're turning that mechanical energy, which was pressure, you're losing it and turning it into heat because of all the mixing that's happening in the wake of this bump that's basically happening. So you're converting, you're not losing energy because we can't lose energy. Energy is conserved, but you're just losing mechanical energy because of all the mixing that's happening in that wake. Right? You've seen like a rock sitting in a stream. Behind the rock, that's where you get your rapids. It's the same thing here. You're going to get basically turbulent rapids mixing in the wake of this object because your fluid can't stay attached. Whereas this case, when your channel is more gradual, you're not going to get the same wake behind it because the fluid's going to come up here and going to be able to stay kind of on this surface for longer. And there will probably still be some wake, but it's not going to be as bad. So we lose less energy to friction. We have less headlands. So you can see that if you look at the table 8.3 at the bottom, you can see some of this effect, like what's happening to the K value at different angles. Basically, as we are very gradual expansion we have very few losses. But if we have a very rapid expansion, we get boundary layer separation, which basically means the object has a big weight behind it, which gives us more frictional losses. Okay, so it is 1:50. This is going to be due on Monday, so see if you can't. All of the links to the videos and stuff are there if you want to rewatch any parts of it, or just want to watch like all of them because they're super exciting. Maybe it's like Friday night movie night, you can watch some fluids videos. But hope you guys have a good weekend. We'll see you back here on Monday. Keep plugging away at the design projects. And make sure to shout out if you have any questions as you're working through that. Have a good weekend.